I have a new calculator. This is a Casio FX-451 from about 1985. This is very nearly, but not quite, the calculator that I used through school, and this one is broken. So this is one of Casio's best ever traditional scientific calculators. You can see it comes in this very neat little wallet form factor, which means it fits beautifully in the pocket and opens up to show the display and hard buttons on this side, and on this side these are all touch sensitive buttons. This is not the calculator I used at school. The one I used at school is a FX-451M, which is very slightly different. The M had a smaller solar panel and a battery that went with it, so it would run in the dark. This one just runs off solar power. If you cover the cell, the display goes blank. But this one should function exactly the same way as my beloved 451M. I loved that calculator. It got me through GCSE maths, physics and chemistry, and A-level maths, physics, chemistry and further maths. People who've been watching my channel probably know that I'm not really very good with numbers, and this thing would sit in one corner of my desk, and it was basically a prosthetic brain. I got so good with it I didn't even have to think about it anymore. I would just think of an expression and my hand would move over to the calculator and make it work. I do still have that calculator somewhere, I just can't find it, hence why I recently bought this one off eBay. As I said, this should function exactly the same way, and it's even broken in exactly the same way. So people who grew up later than I did may not be aware of what I call a traditional calculator. They're probably mainly used to algebraic calculators, where you type in an expression frequently displayed in a dot matrix display, and then you evaluate the expression. This style of calculator instead executes expressions on the fly. So if I do, for example, 1 plus 2 plus 3 equals, you saw that the 1 plus 2 got an intermediate result of 3. Even though the expression parsing is really simple, this thing has a huge amount of functionality. Along with simple arithmetic, it's also got the usual scientific calculator extras such as logarithms, exponents, 10 to the x, e to the x, roots. There are shortcuts for square root and cube, 1 over x, exponent, cube root, and a full set of trigonometry functions. Why I haven't been demonstrating any of the functions over here is because this calculator is broken, and these calculators all break in exactly the same way, which is that the ribbon cable that connects the buttons over here to the calculator body, which runs down this hinge, which folds, always breaks. So as it stands, this is not actually a very useful calculator. So what I am going to do is to try and repair this calculator in the most ridiculously over-engineered way I can think of. But first, let's take it apart. It doesn't have an off switch, so I'm just going to leave it. Sorry about the glare. And I believe, I never took mine apart, I believe that this metal faceplate should just spudge off. As I say, I never quite dared to do this with mine, even though I was a moderately destructive teenager. That's actually spudging quite well. And there we go. And I have not actually seen inside one of these before. And I am actually extremely excited. The reason why I'm excited is that this is the chip that makes it all go. And this is not a blob chip. Usually these things have a cheap and nasty chip on board, a piece of silicon that's bonded directly to the PCB and then slathered over with epoxy. It's a very cheap and effective way of mass producing PCBs, but it means that there's no way to identify or even get at the chip. But this has a label. It's an HD 61708. And that actually sounds familiar. That might be the chip that's in my Casio programmable basic calculator. So I'll need to look that up later. But let's move on from there. So the ribbon cable connects down there. Here we have, it looks like there's metal shielding in there. There's a spring here that pushes up against the metal there. So yes, that will be shielding the chip from the outside world, or I suspect more accurately, shielding the outside world from the chip. That will be an RF thing. Here is a hard plastic chassis. And here is the dreaded ribbon cable. I'm wondering if there's any way to dismantle this further. So my calculator, when it died, you could coddle it into operating again by pressing down here, and then the buttons would work. So mine probably had a crack in the ribbon cable somewhere over here, but this one does not. So I suspect this one is more broken inside. And in fact, now I look at it, you can see a bulge here where the ribbon cable goes, which now I know it's there is incredibly obvious. And I must have spent a good 10 years not seeing that. Oh yes, did I mention it lasted me through university as well? It did go a bit weird in my final year when I accidentally left a pot of garlic mayonnaise in my jacket pocket from the fish and chip shop and sat on it and didn't realise, and it spread garlic mayonnaise all over the vinyl. And then about a week later I actually discovered it covered with rancid garlic mayonnaise, and after cleaning it off, the vinyl was never the same again. Okay, let's try and unstick this. Ah yes, old brittle plastic. It's great. I should add that my plans for this do not involve putting it back together. Okay, so that has exposed a piece of Kaptan tape that was apparently holding it all together. There's the ribbon cable, which then goes through the hinge into the membrane on the other side. Let's stop there for now, and let's take these screws out. Is that stuck down? It's not coming loose. It might be glued. That's the screen, labelled 6H105A, and in there you can see the solar panel. Aha. So over here we have the buttons, which, as usual for Casio, are these very nice double shot things. They're not clicky, they're just pushed down on the rubber domes over here, but they are responsive and satisfying to use. This rubber pad pushes this black plastic membrane, which will be graphite coated on the bottom, and will push down, there we go, onto the keyboard pads, which are graphite covered. You can see that it's divided into segments, and these are contacts to the PCB. So you have your standard row column matrix thing for dealing with a keyboard. There are 1, 2, 3, 4 rows and more columns. Here is the ribbon cable that connects to the screen, which I need to be very careful of because it will pull off. And you can see from the wires, well, and the fact that there is in fact a chip on this side of the board. The board is double-sided, which is very unlike modern calculators. Have I actually managed to break the ribbon cable? It is still connected, but I'm not sure it's electrically connected anymore. That's okay, I knew this was going to be broken. Okay, I want to get this piece of plastic off. I'm not sure I should take this piece of plastic off because this is mostly what's holding the thing together. But basically I want to get the PCB out. So I want to see what's on this side of it. Yes, there is in fact a sticky pad in there that's holding it together. So given that this is no longer electrically connected, this piece of plastic which is connected to here is surplus to requirements. And that should make it much easier to work with. So this is the keyboard. It's a membrane keyboard with, yeah, you can see there's a top and a bottom. I now wonder how the top and bottom are connected, because the way these work is when you press one of the keys, it pushes the two membranes together and makes an electrical contact. So you need a connection to both sides of the membrane. It is very well glued inside this wallet. They are stuck. Yes, that is just a piece of plastic. There are no electrical connections there. So the only connections must be on the bottom layer, which is this piece of plastic. So I did forget to turn the camera on, but I noticed that this is not actually connected to the back of the keyboard. So I cut it open, and look, there is copper-colored plastic. So let's cut that open some more, revealing the keyboard. So that sheet of hard plastic is clearly the backing pad for the keyboard, the thing that makes it rigid. And these are clearly the row conductors for the keyboard. The other side of the membrane will have conductors running this way. So that does tell us that these connectors here are the rows. Now, unfortunately, the other side of the membrane is glued to the actual keyboard surface. But let's do this the brute force way. Let me emphasize, this calculator was already broken. It may be more broken now, but it was broken to begin with. So under this piece of tape, aha, there we go. This stuff is horrible. There is the ribbon cable connecting to the membrane. So we've got 1, 2, 3, 4, 5, 6, 7, 8 rows, and these 4 connectors must be the columns. This will work the same way that all row column keypads work. The microcontroller will energize one of these in turn, or possibly one of these, and then look for a voltage on one of the corresponding columns. It will cycle through this very rapidly, like 1,000 times a second, and will allow it to sense every single key on the keypad with using a minimum number of wires. In fact, given that there are 8 rows, these are the things that will be energized, while these 8 will be wired to a single 8-bit I/O port on the microcontroller. So detecting a key, assuming that these all pull high, is a matter of grounding one of these and then looking to see if the value being read on the port is anything other than FF. If it is other than FF, then that means that that particular column has a key pressed, and you can tell which key by which bit is set. Okay, that is fine. In fact, you see these dark marks running down here? Those will be the columns. And yes, these 4 here are connected through. Good. So we can figure out what all of these do. Okay, let's turn my attention to this. This keypad will work the same way, although with a rather more complicated layout. These connect to the PCB permanently. See, that connects there, so that when you press one of the keys, it pushes this against the conductive pad and will connect these 2 pins together, and which is how the calculator knows the key is pressed. This is the on button, and this is different. See, this has a zigzag pattern. Pushing the pad down will connect the 2 lines of the zigzag together. If I connect those together, the screen should come on. And simply do this. Nothing happens, which is interesting. Can you make out just? Yes, there is a 0 there. The polarizing filter that's needed to make the LCD visible is not glued to the screen. It is in fact this piece of plastic. So if I were to short these 2 pads together, okay, the screen flickered. It does think I'm pressing a key, but that key clearly doesn't do anything. Let's try these 2. No? I thought that would be a number key. Right, that's a number key. That's a 5. So this will be a 1. There we go. Touch these 2 together to reset. Okay, so I think I understand the keyboard pretty well. Now, I want access to both sides of the board, but thinking about it, I don't think it would be a good idea to remove the PCB from the chassis, because that will put strain on this horribly fragile mylar connector. So I think what I'm going to do is to try and cut the chassis itself. Wow. What plastic is this? Okay. There we go. Beautiful and elegantly done. From looking at that dodgy ribbon cable, the bottom 4 were the columns, and they are connected through 1, 2, 3, 4. So that's 1. That goes through to the other side of the board. That goes up to one of these pins. Some of these pads have been coated with graphite and some haven't, which is interesting. But it does look like there are test pads for all of these. That one is there. That one is there. Oh, this isn't connected to the edge connector. Yeah, I think all of these things are for testing the keyboard. This could well be for testing the power circuitry. And let's just do a quick test to make sure it still works after all that wrenching around. Yes, it does. And incidentally, if I turn this over, we get dark mode. This is an annotated photograph of the bottom of the PCB. After staring at the photos, tracing tracks, and in some cases resorting to the multimeter to beep stuff out, I have managed to figure out what all of these various tracks are connected to and what combinations of row and column produce each button. And this, fairly straightforwardly, leads me to this, which is the keyboard matrix expressed as a spreadsheet. So here are the 8 columns. Here are the 4 rows that came from the keypad on the right-hand side of the wallet. There turn out to be 3 more rows which are used by the keys on the left-hand side of the wallet. All the keys are used except for this one. So it'll be interesting to find out what that does. It might be a power off button to go with the power on. Not sure, we'll see. Looking at the PCB in more detail doesn't reveal that much that's interesting. This is an incredibly simple device. The other side of the board shows the chip and more tracers and all these handy test pads. Over here on the left, you can see the connector to the keypad on the right-hand side of the calculator. These are all covered in graphite to prevent problems with the copper corroding. You can see that these copper pads all look pretty grubby. Up here in the top left corner, there's a bunch of analog stuff, which has got to do with power control. This pad here is connected to one of the power button tracers on the other side of the board. So presumably this is how you turn it on or reset it when it's hooked up to the test jig. You can see there's I think that's a resistor. It might be a moving capacitor. I haven't bothered to trace these out. They're not of great interest to me. And that brings me to the chip, the HD61708B04. I know this is a Hitachi device, which I know both from the logo and because I've run into these before. The B04 at the end indicates the various options the chip has been built with. However, the HD61708 bit is considerably more obscure. There are 2 references to this on the internet. One of them is a description of this very calculator, and the other is a Chinese court order because it's the license number of somebody who was done for taxiing without a taxi license, which is interesting but not particularly helpful for me. Now, there is an HD61700. It's used in a bunch of Casio devices, including this PB1000 pocket computer. The problem is it's a significantly higher end CPU than I was expecting. It's an 8-bit CPU with external address bus and so on. This thing can be programmed in machine code. It's also used by this, the Casio AI1000. If I go to the translation, this runs Lisp and can also run Basic C or Prolog by attaching program cards. So yeah, this is a sophisticated 8-bit processor. This is vastly overkill for this device, and I'd be very surprised if it actually had one. I would expect something more along the lines of this. This is one of Hitachi's ubiquitous 4-bit microcontrollers. You can see that the model number is pretty similar to the one in the calculator. These are all 4-bit computers, so they deal with registers which are 4 bits wide. This one has 4K of ROM for instructions. Each instruction is 10 bits wide, and 256 digits of RAM. Of course, a digit is a 4-bit wide value. This thing doesn't do bytes. The RAM is also used for video memory for the LCD controller, because of course you need an LCD controller. It's also got 32 I/O lines, which is, ideal for dealing with a keyboard, and the ability to do BCD arithmetic. It consumes almost no power, and it is dead slow, i.e. perfect for a calculator. However, I know it's not this one because the pinout described here is clearly wrong. All the analog components are connected down here on the left, which on this is all I/O lines. 4-bit microcontrollers are deeply weird. The documentation describes the register layout. It's got 6 4-bit registers, which is A, the accumulator, B, the other accumulator, X, Y, SPX, and SPY, which are used for indexing, and a collection of the usual CPU flags. There are 2 index registers because, of course, if you've got 256 nibbles of RAM, but your register size is only 4 bits wide, you can't address them all. So the RAM is arranged in a grid where the X and Y registers correspond to the rows and columns, or now I look at it, columns and rows. So to read or write any particular nibble from RAM, you have to set both X and Y, and then you can do your indirect read. 16 nibbles are directly addressable by instructions, which simplifies things, but still, doing anything interesting with this is particularly weird. Even weirder, if we go up here, we look at the program counter, which of course has to be wide enough to access all 4K words of ROM. It's divided into pages and addresses within a page, so it's a segmented architecture. But the address part, the address within a page, doesn't increment consecutively. This is the order. So it executes the instruction at word 63, then 62, then 61, then 59, then 55, and so on until you get down to 31 here, and then it loops back again to 63. The documentation here doesn't explain why it does this, but chances are it's to reduce the amount of silicon needed to add 1 to the address, which gives you an idea as to just how stripped down these 4-bit CPUs are. But of course, I have no idea whether this actually is one of those. I can't find any information about this, and honestly, there's probably nothing we can do with it anyway. The code will be in ROM, the ROM will not be exposed to the outside world. There just aren't enough pins. Now, I have found exactly one pin, this one, that doesn't seem to be connected to anything, so it might be worth probing that. But honestly, I doubt there'll be anything interesting on it. But anyway, let's move on. So using my newfound knowledge, I know that if I connect RZ, which is this one, trying to make this visible, and C, can't remember what it is, but it's this one, I should get a 8. And we do. 8. And if I connect RZ, which is that one, and C1, which is down here, we get our mysterious key. So let me just hold that down here and touch here, and if you look in the top left of the screen under the Captan tape, it's a shift key. So it's exactly the same as the key up here. Well, that's not very interesting. But it does demonstrate that I understand the keyboard. Unfortunately, I do have other problems. I do have a plan for this. I'm not just randomly smashing it up. I want to rebuild this into a calculator I can actually use. And off camera, I've been doing some mocking up and prototyping. And the thing that's come up is that I can't work with this geometry. The PCB here sticks out below the screen, which is fine for a device that goes flat, but I don't want to do that. I want to have the screen angled up so I can see it from a desk. So I need to somehow move this out of the way. And I think that what I'm going to have to do is to disconnect the PCB from the plastic chassis so that I can bend the flex connector. And I don't really want to do that. The flex connector is fragile and very difficult to repair if it goes wrong. But let's have a look and see what makes this go. So I think something is sticking in here. I can hear the adhesive slowly coming loose. There it goes. Right. There's another bit on the other side. And there is the flex connector. Yeah, I can work with that. that's it done. Let's just check to see if it still works. Turn on the power supply. You may have noticed these wires I soldered on. And oh, thank goodness it still works. Okay. So what I'm planning on doing is mounting it like that, which will both show off the chip, keep the board flat, and make the screen nicely visible. A bit of work with a 3D printer later, and I have this gruesome pile of waste plastic. But more importantly, I also have these plastic clips. And these allow me to position this just right. I want that one. And this holds the board together, like so. And it's decently robust. For the time being, I will just hold it together with a rubber band. Right, but what am I going to do with this? Well, that brings me to this glorious piece of laser cut acrylic. Doesn't look like much because it's still got the protective film coating on it, but this is the chassis of the thing I am actually leading up to. Because what I'm going to do is fasten this thing down here, insert key switches everywhere, and I will end up with a big chunky desk calculator that I can actually use. If you've never seen laser cut acrylic before, you end up with these beautiful melted clear edges. They look really nice. It's so much better than actually cutting or drilling. But anyway, the first thing I need to do before I can start fitting anything is to peel this off. Yeah, turns out that was just the sticky label. I haven't managed to get the plastic film off, which protects the acrylic from scratches. There we go. So now I just need to mount the thing. I was originally going to use self-tapping screws through the holes in the clip, but that turns out to work not so great with acrylic. So instead I'm going to use some, I believe these are M3 bolts, and just clamp it in position with some washers. So, all right, that isn't working. I am going to have to design some clips with holes in the right place. Be right back. And here we have the new clips. So let me just attach this one, which slots in here. I also took the opportunity to adjust the angle of the screen a little, since I was printing them again anyway. That fits in like that. And then this one, which has a little cut out here because of this surface mount capacitor. That goes on here. Okay. So now, hopefully these holes will line up. Oh good, they do. So I should just be able to put the bolts right through. Yes, that is much more satisfactory than the previous plan. Excellent. That's just finger tight, because I'm probably going to want to dismantle this again, and that's decently solid. Get rid of a filament of hair. Good. Okay, the next thing to do is to attach all the key switches. And these are just simple friction fit. They just push in. They're reasonably solid. I could always glue them in if I wanted to, but I don't think I will. And now I just need to go through and attach all 56 of the key switches. I have a bag. Here we are with all the key switches in place. So this is approximately how it will look once it's finished. I didn't quite order enough of these. I have more coming, but until then I'm using these as a stopgap. These came from a terrible old keyboard I have. The key switches are cheap cherry red clones, so they're linear, which I quite like, and I think will go well with a calculator like this. It's still big and chunky, feels decent. I need to put these caps on. These are supposed to take little labels that go underneath these transparent caps, but I am going to wait until I know more before printing and making those, because it sounds like they'll be a total hassle. I'd really like to have like proper keycaps made, but that looks difficult and expensive. It's pretty obvious that one of the next things on my list is going to have to be making the feet. The key switches stick out below, and whenever I put it down onto something, it tends to push the key switches out a bit. One important thing is, if I can figure out where I put it, embarrassingly, I can't lay my hands on it right now, but the solar cell will probably end up being mounted up here. I was originally planning on running the thing off a 3-volt button cell. However, my own calculator had an off state. That ran off a combination of a smaller solar cell and its own battery. This one, being a pure solar cell device, doesn't have the off state, which honestly makes sense. Energy is free. So running it off battery is probably not a good idea, as it would go flat very quickly. And given that I already have the solar cell, or at least hope I have the solar cell, I assume it's lost somewhere on my workbench. Somewhere. Since I have it, I might as well use it. Fresh off the 3D printer and still smelling faintly of hairspray, I have 4 feet. The way these work is there's a hexagonal slot which holds a M4 nut captive. A bolt then goes in this side, goes through the nut, does up, and holds the foot in place. This side is slightly slanted to hold the keyboard at an 8-degree angle. 8 was... yeah, I think these switches are a little bit loose. 8 was picked more or less arbitrarily. We can push the bolt all the way through. More or less arbitrarily, because that seems to be roughly what keyboards tend to be set to. So, yeah, I took those felt feet off. Those were a bad idea. I needed to use quite a lot of IPA to get the stick off the plastic. What I should have done was make temporary feet by just putting one of these bolts through and then doing the nut up. But anyway. That wasn't captive. That will explain. Let's try and push this all the way through. That will explain why nothing was happening as I was doing the bolt up. So I do need to rotate them until the slant is pointing in the right direction, like so. that goes like this, which I realize on the camera is not going to show up at all. Okay. Now I just need to repeat it with the others. That's about right. And it sits very happily on 4 legs. It's a bit bendy in the middle. You shouldn't really be pushing hard on the keys anyway, but that has worked out quite well. I appear to have made a bit of a boo-boo. Off camera, I decided that the key switches were not friction fitting well enough, and so I added a drop of glue to each one. The glue was super glue. I mean, it worked, the key switches aren't coming out, but it's also done really weird things to the acrylic, which is this white stuff. It does seem to come off if I use IPA, at least to a certain extent, but yeah. I do have a piece of acrylic spare, so I can trivially recut another piece of this. But now I'm wondering if whatever the super glue put on the acrylic, I think the solvent attacked it somehow, may have also left residue inside the key switches. If so, the key switches are useless. So I am gonna attempt to clean this, and then I'm going to have to test every single key switch. Also, the next stage was supposed to be to solder on all the wires. This is supposed to be one of the rails for the vertical columns. Once I've soldered the wires on, the key switches aren't coming out. Because geometry. So in addition to that, I'm wondering whether I should invest in a pile of key switch sockets. I mean, once the switches are glued in, they should not be coming out again. But given my general level of goodness at doing manual things, making it so that I can disassemble it might be a good idea. Results are inconclusive. Some of them work, some of them seem not to work, some of them seem to work intermittently, and I can't tell whether that's because I'm having trouble making contact with the pins or whether the switch itself is faulty. I think this was one of the non-working ones. Well, now it works. That one works. There we go. I do have a bunch of spares, so I'm slightly conflicted about whether to just order another bag, it's not like they're expensive, or to try and identify the dodgy ones and replace them. However, another thing that's come up is the acrylic's cracked. It's a little hard to make it show up on camera, but there's one. There's some in there. There's one here. Is that showing up? This is probably all hopelessly out of focus. Trying to focus on transparent material is not fun. And I can't tell whether this is caused by glue damage or it's just me manipulating the sheet. So I think it's fair to say that this particular sheet of acrylic is a write-off. Looks like there will now be a long delay while I do an order from China. It's several weeks later, and my new key switches and keycaps have arrived, which is nice. I now have enough key switches to repopulate the chassis, plus enough keycaps to, go on the key switches. Along with the switches, I also ordered some sockets. These are surface mount key switch sockets, which should make assembling and disassembling the thing a whole lot easier. except for one small problem, which is that these are the wrong ones. So focus might make it a bit hard to see what's going on, but it looks at first glance like these will fit. You see that these two holes here are arranged the same way round as these two pins here. Unfortunately, what I didn't realize is that this is the bottom of the switch. They actually plug in the top. And not only are these arranged the wrong way round, but if you can just about make that out, they are in fact a little bit too close together. Because these are sockets for Kyle chocolate key switches, while these are MX clone switches. So several weeks after that, my new sockets showed up. These are actually MX sockets. You can see that they are laid out differently to the Kyle sockets and the holes are slightly further apart. And that means that I can, this is all very small and hard to show on camera, plug the two together. That's the wrong way around. Let's try it this way around. Like so, and they just go on. The plan now was to get some sort of rigid board. This would then be mounted underneath the chassis. These would then go flat onto the board so that the board was supporting them. The switches would then push through the holes in the chassis into the sockets. The sockets would keep the switches in place through friction. They are not very firm, but they're good enough. That would let me make the holes in the chassis slightly oversized to avoid stress on the acrylic. The board would support the pressure of pushing the keys. Everything would be much more rigid. Everything would be much more serviceable and life would be good. Of course, actually placing these things, which are small and fiddly, into precisely the right place on the board would be annoying, and as would wiring them all up. Until it occurred to me that my underlying board was basically a board with, circuits on it. Some kind of circuit board. So I had these made. These are PCBs from JLC PCB, who aren't sponsoring this video, but probably should be. The idea is that these contain all the necessary mounting holes to put the sockets into, all in the right place. So soldering it all together should be easy. They're good and solid. They're 1.6 millimeter. They're already wired up. This should make life much easier. That is assuming they work. You may notice that there's actually quite a lot of these. You have to get them made in units of 5, and they're quite heavy, and shipping from China isn't cheap for these. So these are quite pricey. So let me open it up and actually see if it's the right size or if I made some kind of mistake. This is all for real and non-scripted, as you might be able to tell. Okay. Here's a PCB and I can immediately see one major cock-up. The problem is these holes here. This is for the keyboard matrix and this is the dedicated connector for the power button. These are supposed to be 0.1 inch spacing, which is the standard size for pins. Except I managed to use the wrong footprint, so they're all too small. I think this one is maybe 1 millimeter spacing. These squares on the workbench are a centimeter. So that's 1, 2, 3, 4, 5, 6, 7, 8. Okay, it's not a round number in millimeters. Right, that's really irritating. Soldering these in is going to be wires now. I don't think I have any pins small enough. I don't really want to get these circuit boards remade. It would take another several weeks and also be moderately expensive. Okay, let's try the socket and see if that works. So here is the back. You can see the footprint for the socket marked out in white. So these go into place. Oh, good, they fit. There's enough pad there to make them manually solderable, even though they're surface mount. The key switch should then just plug on. That works beautifully. Yeah, that'll work. So that's really, really irritating. Rummaging through my drawers, I did manage to find this connector, which is the right pin spacing, although it's the wrong form factor for this. But seeing that next to this 0.1 inch standard pin header shows you just how small these things are. Well, I suppose I have been getting a lot of practice in tiny microscope soldering, what with the smartwatch project, so I may give this a go. This is 0.05 inch, so it is exactly half the size of the existing 0.1 inch header. Fantastic. At least this means that a piece of ribbon cable will go on nicely. So at this point, I think the only thing I can do now is to solder it all up. And you know what that means? A time lapse. Just as I'm getting prepared to solder this IDC cable in, I discover something interesting. This is 1.27mm pitch, that is 0.05 inch. This is not. This is very slightly bigger. If I compare against standard ribbon cable, which is what I was expecting that to be, let's try it from this end. This matches. This is 1.27mm pitch. This is not 1.27mm pitch. So I've managed to destroy this DuPont connector cable for nothing. The reason I wanted to do that is because I wanted to add connectors for pin headers on the end, just to make everything easier to work with. And trying to crimp on 15 crimp pins onto a piece of ribbon cable is not my idea of fun. Plus, I kind of want it to work. So I'm going to have to think up something different now. This is not working. The ribbon cable is the right pitch, but actually trying to solder it through these tiny holes is way too hard. I've done some of it, but I don't think that it's just going to work. I think I've shorted some stuff together and it's just horrible. So I get to start again from scratch. Shame, really, after crimping all these DuPont connectors on. Well, that was miserable and time consuming, but I think it did actually work, and I only lost one wire. One problem with using this solid core wire is that as you bend it, metal fatigue can cause it to break off down here at the solder joint, which is what happened. So I'm not quite sure how many of these will actually survive up to the actual product. But anyway, that now is all wired up. So all I need to do is do all the rest of the project. Well, that took a bit of time, but was pretty easy, especially compared with these god-awful wires. I only placed some of the key switches because halfway through doing this lot, it suddenly occurred to me that I am going to have to put the acrylic shell over the top of this between the key switches and the PCB. So I'm just going to have to take these off again, but there are enough here to at least test it. So let's do a simple smoke test. Plug in a couple of DuPont connectors into the wires for the power button, switch button thing. And hook it up to the multimeter. Set it to beep mode. If I press this key, nothing happens. Oh dear. Ah. That's not plugged in correctly. Try this one. Okay. See? No camera tricks. I'm doing this for real. Interesting. Why did it do that? Why isn't it doing that? If I short the two pads together. Okay. If I pull the key switch, find another DuPont connector, and short these two together. Nothing. Ah. Okay, it's soldered down, but the key switch wasn't working. Why wasn't the key switch working? Dirty contacts? It seems to be fine now. Let me try a different key switch. I do have lots. Because if it is dirty contacts, okay, well, weird, but it does actually seem to work. Ah, Vox. So much crimping. No. Wire blob has vanished. Wait, hang on. Are also wrong. Wait a minute.